Brian the cast, and I was the experimenter for this lab.
I'm David Montgomery, and I was the recorder.
And I'm Stephen Haim. I was the layout designer of this lab. And this lab is optical collimation and radius of curvature tests with this year.
So for parts A and B of the lab, basically we were just repeating from last week's lab in the setup. Basically, again, we're building a beam expander, and of course we start with a laser, and we use the pinhole method to make sure it was aligned. So there's 3 degrees of freedom on the stage that's holding the objective, and 3 translation directions for the spatial filter itself. Basically, we move those to make sure it's aligned, and we know that it's collimated when we basically see a bright spot and no diffraction orders. And then we can add the achromat. We chose the 250 milliliter focal length, and basically our beam expansion ratio would be a ratio of that focal length and the objective, which is 9 millimeters, leaving about 27.76 for our beam expansion ratio.
So this is part C of the lab, and what we're doing here is we're trying to measure the focal length of this mirror over here. And what we did is we flipped our shear plate around, so now it's not testing whether if this beam's collimated. What it's doing is it's just shooting the laser through this, and then the mirror reflects it back, and it's testing whether the light reflected back on the mirror is collimated. So what we did here was we measured the angle the fringes were at and the spacing of the fringes. And as you can see, when you move this, because this is a flat mirror with almost no power, that the fringes stay pretty much the same no matter where I move it. That's because L is not dominating the system. So we want to find the radius of curvature in order to find the focal length. So what we did is we assumed we had a 10 millimeter shear plate, and we were able to calculate S from that. Once we had S, we could use the D value that we measured, the distance between fringes, and the alpha value, which is the angle the fringes take. Once we had the radius of curvature, we could plug it into this equation here to find the focal length of the mirror. And as you can see, as I was talking before, the distance in L was doing absolutely nothing, so this is how we know that it's a low focal length mirror. We calculate the focal length of this mirror to be somewhere on the order of 100 meters. Just a quick note, I wanted to stress the fact that alpha is measured from the horizontal line on the shear plate. So something we learned about while taking measurements, if we change D by just 1 millimeter, our delta R changes by 40 meters, which is a huge deal. So you have to be really careful when measuring the distance between the fringes, because it can really affect your final result.
Alright, this is part D of the lab, and we're testing this low power lens with our system from part C. Basically what we did, instead of putting last time we put a mirror on the right side of the shear plate here, this time we're putting a lens on the left side, that way we can see the fringes here in the shear plate. And so this is a low power system, so we're expecting a high focal length, and what we ended up getting was 54 meters. And the way we found this was we determined the fringe spacing here and the angle compared to the reference line. And you can see, go ahead and look at the shear plate. When I move the lens, you don't really see much going on in these fringes. You see some shifting, but that's probably because of stability loss in the system, because I'm creating vibrations on the table. One of the things you could have done wrong in this lab is you could have put your lens in wrong. And so you can see on the shear plate here that we have lots of spherical aberration. And as I try to find the collimation point, you can see you have some strange S shapes, I guess. And so if I just flip the lens around the other way and reposition it, you can see that the straight line fringes are much more easily obtained.
So for part E of the lab, we were basically testing the radius of curvature for this mirror. This mirror is curved, so it's not the same mirror that we used in part C. A couple different things about this setup. We also used a high quality reference lens, so it's also not the same as the lens in part D, which by the way had a big smudge. And basically we keep the same setup from what we set up from before. The 2 important things about this is we basically want to find 2 points where we see collimated fringes. So basically by slowly adjusting it, you'll see at one point we get collimated fringes, and you can tell because it's parallel with the reference line on the shear plate. This is the point where the mirror is at, where the focal length away from the reference lines. Now we slowly want to move back again, and again we'll find collimated light according to the shear plate. If I can find it. Yeah, here we go. So again, we find a different spot where we see a collimated beam, and